All right, last time, what did we talk about? Oh, it was a long weekend. I don't even remember. Don't worry, got you covered. Last time was modular arithmetic. The start of number theory. And today, we are going to be doing a little review of this, and then stuff about primes. How cool. So, let's get into it. Start by reviewing modular arithmetic. And I'm gonna do, a more generous review than usual. So it's gonna, we'll give it a good few minutes. So recall, we say A is congruent to B mod M. So we write this triple equal sign, and we say congruent if, so when we defined this originally, there are a number of different, there's a number of equivalent conditions that you can use to define it. But I'll just remember one of them right now, which is if A and B leave the same remainder divided by M. So for example, let's just come up with an example off the top of our head. 25 is congruent to 45 mod 10. Because when you divide by 10, the remainder is 5, both times. So the division algorithm, or the division theorem, aka division algorithm, tells us, in particular, I'm not going to repeat the whole division theorem, but remember one consequence is that every number is congruent modulo M to exactly one of the following. Basically 0 through M minus 1. So we define this set to be Z slash M, which we say Z mod M. So we're just giving it a name. And remember, another theorem that we talked about last time says that if we think about this set of numbers from 0 to M minus 1, we have a well-defined way of adding them together and multiplying them. And this is what we mean by modular arithmetic, essentially. So something that I didn't say last time that I want to bring up this time in case it's helpful, a common analogy that you'll hear is that you can think of this like a clock. So in the same way that as the hours keep going by, which way is it? I don't know, maybe this way. Eventually, you get back to where you started. And that's the same way that modular arithmetic works, essentially. So an example of that is if you start at 8 a.m. and then 7 hours later, that's equal to 3 p.m. And this is essentially the same as you would think about 8 plus 7 is congruent to 3 mod 12. So we're working mod 12 because there's 12 hours in the usual 12-hour clock. And maybe just to point out the slight difference, when you're talking about a clock, you normally use 1, 2, up to 12 instead of 0, 1, up to 11, but it's essentially works the same. you could change this set out for some other set and still have it work, but we just use this one for, uniformity and convenience. And remember that there was this nice application that we can translate equations in the world of integers to the world of modular arithmetic, and then examine them there and see if that tells us anything. We call this reduction mod m. So let's do a quick example of that. I have this equation, 36x squared plus 45y cubed equals 87. Okay, and I want to know if this equation has any solutions in integers, and I want to start investigating that by looking at in the easier situation of mod m. So in this case, I'm going to reduce mod 5. And so what do I need to do this? So I need to look at all the coefficients and basically reduce them mod 5 in the sense of finding the representative in this set. So 36 is congruent to 1 mod 5. 45 is congruent to 0 mod 5. So I hope it's clear how this is working by now. But of course, this is because it's 35 plus 1. 35 is divisible by 5. 45 is divisible by 5, so it's 0. And then 87 is 2 more than 85. So it is congruent to 2 mod 5. So the equation becomes 1 times x squared plus 0 times y cubed is congruent to 2 mod 5. And now, real quick, let's just check for solutions. You can see it's very nice that we got rid of the y cubed term entirely. So this is just 0, which will make our analysis easier, which is nice. And so let's do the same thing we did in the mod 4 case. Let's examine what our squares can look like just by computing them. So in Z mod 5, let me just not write mod 5 everywhere, but that's what I mean. 0 squared is congruent to 0, 1 squared is congruent to 1, 2 squared congruent to 4, then let's see, 3 squared is 9, which is 5 plus 4. So that's again congruent to 4. 4 squared is 16, which is 15 plus 1. So it is congruent to 1. So squares are 0, 1, or 4 mod 5. And this equation is asking for a situation where x squared is congruent to 2 mod 5. So there are no solutions. And remember, what does this tell us? So, no solutions to the original equation no solutions to this original equation either, because if we had a solution, we could reduce mod 5 to get a solution to this. So since that's impossible, we conclude that there are no solutions. So one more quick note on this, in answer to a question. Why do we choose to reduce mod 5? This is a good question. And the idea is that you can choose to do different things depending on the situation. So partly this is just another example with a different m, but in life, let's say, you're given an equation and you want to investigate whether it has solutions or not. No one's giving you a particular thing to reduce. You might want to just experiment with different ones yourself and see if any of them tell you anything. And maybe there are some ways that you could try to pick them. Like, I kind of did this on purpose, that cubes, you know, if you look mod 5 and you look at what the squares are, they're only 0, 1, and 4. This is very nice. But cubes do not work like that. I think every number is a cube. Like, everything mod 5 is a cube. So this term we can't deal with in the same way. But we're reducing mod 5, so the coefficient becomes 0 and it knocks that term out. That's very convenient. So you might want to think about these kinds of things if you are ever confronted with an equation. There are many different ways to reduce it, and they will tell you potentially different things. Right. So that is another example of this nice application of reducing equations mod n. And this, I think, will conclude our little review.